Okay, the last topic that I'm going to talk about is correlation. And correlation is a very popular measure. Or actually, a sample correlation coefficient is a very popular measure of relation between two random variables. And I left that to the end because I would like to also talk about the corresponding population parameter correlation. And now when it comes to this topic here, this time we are not going to be assuming that X is a mathematical variable. They are going to be controlling it, but we are going to leave it, and X and Y are both going to be random variables. Therefore, they are going to be joint distributed. So at this point, actually, there might be some confusion. So I'll try to recapture what we have been talking about in terms of statistical models and their relations with observational studies and control studies. When I say control studies, I have mostly used the term randomized studies, actually, studies using randomization previously in the previous chapter, because actually we were only concentrating in a single random variable. If on the other hand there is a mathematical variable here, which for instance in regression we have used manipulated variables x values and some y values, then the corresponding study will be called a control study. So what do I mean by all of these? Now, think about two different scenarios. In the first scenario, I'm going to be manipulating a flow rate. I'm going to bring it at certain levels, and I'm going to be measuring the corresponding concentration. This is if I have this power over X to be able to manipulate this at will and measure the corresponding concentration and then come up with a graph related to X and Y, a figure like this, and come up with a linear regression model, then of course, obeying the randomization rules, the other randomization will still have to be performed, but I conducted the experiment at certain specific values of X. In this case, this is going to be a mathematical variable, not a random variable, but a mathematical variable, and the levels of that mathematical variable will be determined by the experimenter, whereas this is going to be a random variable. And the randomness comes from, due to this model that we write here, it is going to be beta 0, beta 1, x, or any model that you can, indeterministic model that you can write, plus random error term. This part is fixed by the experimenter. This part is going to be the random error due to disturbances, measuring errors, all stuff like that. So that y is going to be a random error. That was a story that we have dealt with in linear regression. And note that in this case, if you conduct this experiment properly, which I mean proper in a randomized manner, well, note that control experiments, if depending on the number of your manipulated variables or independent variables, there are some certain designs of these control experiments which are basically covered in design of experiments, but unfortunately I'm not going to talk about those. They are pretty much outside the scope of this course. Anyway, once you do these experiments that is going to that it's specified as certain x values, once you conduct these experiments properly and have the corresponding y values and come up with the s parameters estimate in f here function, then you are going to be obtaining a causal relation between x and y. The very important point here, when you perform a controlled experiment, when you do it properly, the resulting relation will be a causal relation. So you can say that x causes, so if this is the model that you come up with, expected value of y given x hat, when you come up with a model like that, of course, these are going to be also the parameter estimates. Given some x value or change in x value, you are going to be multiplying this value and adding this value, and this is going to be the resulting value is going to be caused by x. That's the important point. Our whole analysis was based on this perspective, I may say. Why do I mention this, or why do I emphasize that? First of all, in our analysis, we have taken x to be a non-random variable. If you take it to be a x to be a random variable, then the analysis, the procedure itself will not be valid, because when it comes to, for instance, expected value of x, I have simply written here x, the corresponding fixed value of x here. And when it comes to variance of x, we have taken this to be again a zero value, right? Because x is a fixed value. On the other hand, statistical models are not confined only to controlled experiments. So these are controlled experiments. We should be able to write a similar expression like that relating two variables from observational studies. But in this case, the very important point here is x is also going to be a random variable. Why? Because in this case, let's think about a scenario. For instance, I'm going to be solving a question related with the midterm grades at the end of this lecture. I'm going to be plotting midterm 1 versus midterm 2 grades from a semester, which I cannot remember the semester. Then in this case, the population that we would be interested, call this again x and call this y. So the population, this x will be sampled from all the possible years in the history and in the future of, let's say, from all of my courses I have taken, or from maybe all of the courses that has been taken in your university, whatever you can describe your population as well as you like. And midterm 2 y is going to correspond to that population, but this time it's going to be midterm 2 results. And therefore, I'm going to be taking a single sample here, xi, yi couples from I1 to n. Note that this is very similar. The data collection style is very similar to the data collection style here. For different flow rates, we are going to be measuring concentrations, I from 1 to n, for n number of experiments. The very important point here is, here I determine the xi, or the experimenter determines the xi at a specific value. On the other hand, here I, as the observer, both observe and xi and yi values together. I cannot do anything to determine the xi value or yi value. And since xi values will change from observation to observation, so here each sample or each subject to subject, I may say, and each subject corresponds to a student, right? So if you have 10 students, we are going to have x is going to be the first midterm grades. So x is going to be a random variable. And y is going to be also the second midterm grades of these students, is going to be another random variable. So for this case, note that we cannot determine the x values here. So this is not going to be a control study at the same time, because x is going to be also a random variable. So from that perspective, many of the things that are publicly shown, that you see on the newspapers, on TV, things like that, are mostly, they are observational studies and they are random variables. What do I mean by that? If, for instance, scatter plot the areas of the world countries, a couple of those, let's say, and the populations of the same countries. Of course, this is a bit debatable. And actually, the population, all the areas of the countries, we have probably 200 something or close to 200 countries in the world. So you can actually plot all of them here, but let's keep it to the statistical context that we have talked about. So let's say that we have plotted randomly selecting these countries in an from an alphabetical order, 10 of these countries, and we found their areas, and we have found their population values, and let's say that they are of this form. I'm just making it up. I don't know actually. So in this case, both area and population they are going to be both random variables, because if you take another sample, both these areas and population values would have changed. it is not like the flow rate that I can determine. But just like this one, I can scatter plot these two, and I can come up with again a relation. And that's what this chapter is going to be, what this part is going to be about. And this relation is going to be still the very same relation, or the structure of the model will be identical to this one. But note that the meaning is going to be very important. Now, once we find this model parameters, once we determine estimates of these model parameters, all right, that like that, now we cannot say that when the area of this country is equal to some value, right, this causes the population to be at this value. The causal relation now is lost. There is only the so-called correlation between those two variables. And as I said earlier, as I said, tried to explain in the previous lecture about that, there may be a confounding variable which causes to happen both these variables, both area and population, or midterm 1 or midterm 2 regress, or any other two variables that you might think of. Or there might be what is so-called a reverse causation. Actually, Y may be causing on X. We don't know that. So maybe population causes area, or there is totally something else going on. And there is actually another thing. There might be the so-called superfluous correlation. Actually, there's a nice website related with that. Sometimes totally unrelated events, probably causally unrelated events, if you scatter plot them, you are going to obtain some very nice fittings that you can find. So if you think that they are causally related, they are, first of all, no, they are both random variables. But in those cases, note that even their correlations are incidental, totally coincidental, I may say, not incidental, but they're totally coincidental. So you cannot make any meaning from that. So the moral of the story is, when you don't have, when you have observational variables, and for many cases, it is the for many cases that would be what is you are going to be obtaining as data. The results, causality will never should be pronounced, and even the relation between them, even there seems to be a correlation or a significant regression line can be drawn, still one should be cautious. So that was the opening statement for trying to distinguish between control studies and observational studies, how to include them, or inclusion of these studies in statistical models. Statistical models can be written for both of these studies, but their meaning is totally different. Now, when you have these fixed values, as I said, we have included them in linear regression analysis. In the previous lecture, we gone through the derivations, and X was taken to be fixed. However, as I said, in many cases, X is not going to be fixed. In this case, what are we going to do? That is the fundamental thing that I'm going to be talking about in this part. So let's assume something further. Assume that, that's an important assumption. Furthermore, not only they are jointly distributed, but they are bivariate normal distributed. And this is actually taken from chapter or lecture 5D, I guess. Probably, actually, I'm going to give you the link in the description of the video. This is the very same part of the slide. So we have a bivariate, this normal distribution of X and Y, a bell-shaped thing, but it's going to be three-dimensional. And this is usually represented by these contours. Each of them represents the same probability. If you recall, this is going to be the peak, this peak here, the mode of the distribution. Anyway, so how can we describe this distribution? They are going to be described by marginal probability, marginal mean values, right? The marginal probability, this mean values obtained from the marginal density functions, and standard deviations again obtained from the marginal density functions. So the only parameter that cannot be obtained from the corresponding marginal density functions is correlation. Depending on the correlation, if you recall, the shape of this, or the principal axis of this ellipse had changed. If there were no correlation, then what you obtain would have these Gaussian curves. Okay, I couldn't draw it very clearly, but I think you get the idea. So now the question is, can we somehow combine this perspective with the linear regression approach? Yes, we can. I hope you can also remember this. For those who don't remember, just go back to lecture 5D. Now we have also this without proof, the expected value of y given x is equal to this equation here, these terms here. And the variance of y given x is equal to this equation. Now note that at this moment, that given condition should have rung some bells in your mind, right? This is kind of similar to our approach in linear regression when x was a fixed variable. X is not now a fixed variable, but although it's a random variable, still we have used this. And probably when we are talking about that in lecture 5D, we weren't thinking about whether x is fixed. If x is, of course, a random variable, there was not an issue of a fixed or a mathematical variable versus random variable concept here. And again, this was if correlation is equal to 0, then this part was gone. This is going to be equal to 0. This is going to be equal to 0. So therefore, the expected value of y given x is simply expected value of y, and variance of y given x is simply equal to variance of y. So actually, it means this. If this is again our distribution here at some x value, given some x value, note that still x is a random variable, but given some x value, I can come up with this distribution. The difference between the fixed value is I cannot make sure that experiment will be conducted at that x value. Experiment will must be conducted and x and y values will be produced. That is the difference between the mathematical variable x, which can be on which we can apply fixed values and conduct the experiment at that value, and the random variable of x. Anyway, however, the analysis can be done for both ways, whether x is fixed or random variable. So given that the random variable x takes a specific lowercase x value, then the distribution of y is going to be like this. So the distribution of y is going to be normal distributed with expected value of y given x. Actually, it is this quantity here, right? And the variance is going to be equal to this quantity here. Now, maybe you felt that we are a little bit close to linear regression, but maybe not still close enough. So here is the idea. Can we represent this relation using a simple linear regression model? So I would like to now think about y and x as two random variables, bivariate normal distributed. Can I, as an alternative notation or representation, can I show it in a linear regression model such as this one? So am I justified in writing such an equation? At first sight, maybe it doesn't seem to be that way, because in this case, we do not control x, but x and y are together obtained from an experiment. You just observe. So maybe it seems a bit counterintuitive at first sight, but it is not. Actually, that is going to be our model with the additional assumption that this random error is equal to that one. So I would like to convert the bivariate distribution perspective to x, a relation between x and y with a random error of e representation. So here is the thing. Now, when I take the expected value of this is actually all the previous analysis we have done before. There is nothing new in terms of mathematics here, but the perspective is going to be different. When I take the expected value of x, what I obtain is this result. Now, let's analyze this from this perspective. Changing for different x values, expected value of y is going to change, but in a linear fashion. This is what is said, what this equation says. I repeat again, expected value of y, our other random variable, is going to depend on x linearly. Given some x value, you're going to multiply by some constant and add some constant, and you obtain this value. This is actually this property obtained from the linear regression model. And the second thing is that variance of y given x is simply equal to variance of noise. Note that this means this is not a function of x, which means it is constant with respect to x. Now, if I go back and look here, what does that say? First of all, this term, variance of y, is equal to this one. Maybe you are confused about this term, but it says something else. This is going to be a constant, population constant. This is going to be another population constant. Therefore, this is going to be a constant. Therefore, the distribution of y, its variance is basically constant with respect to x values. So that should be the first signal that, oh, the distribution of y given x may be identical in the bivariate distribution to the statistical model that we have introduced. Now, the second thing, what about this? Now, for this case, we said that this is basically a linear function of x. Now, here we have this representation here. Note that this is a constant. Constant, all of them are constant, except x here. So therefore, if you call all of them constant, this is going to be a linear function of x. So therefore, this mu given expected value of y given x is actually a linear function. Here I use g as any function, is going to be a linear function of x. It's going to be alpha 0 plus alpha 1 x kind of thing. And this is now we have something like this. Expected value of this quantity is equal to this. Variance is constant and it is normal distributed. So these are exactly the very same three properties that we have. Expected value is a linear function of x, variance is constant, and y is normal distributed. Therefore, this representation now can be shown in both ways. Derivation is very simple. I write expected value of y given x, this equation. I'm going to leave x here as a single term. So I'm going to just multiply these terms both by x and mu x. So when I do that, it's going to be very straightforward. So this is going to be expected value of y minus correlation, these terms plus these terms. So if you just multiply, this is going to be the result. Note that these are all constants, expected value of y, expected value of x, variance of y, variance of x, correlation. These are our population values constants. So they're going to be simply equal to beta 0. And this is our three are also constants. It's going to be equal to beta 1. So now here is our nice linear regression model. Expected value of y given x is equal to beta 0 plus beta 1. But that's not, of course, over. Variance of y given x should be also a constant. And this is also a constant. And since y is normal distributed, also, we know the marginal distribution y is normal distributed, right? And also the conditional distribution is, it's better to say conditional distribution of y is normal distributed. Now, and since these are the corresponding parameter values, equivalent expression of the parameter values, both bivariate distribution and its corresponding linear regression, simple linear regression form will be identical to each other. So this is what it says for a bivariate normal distribution. A simple linear regression may be constructed as similar to fixed x and fixed x in linear regression. So that's an interesting thing, which says that linear regression model will be valid, as I said at the beginning, both for controlled experiments with fixed x values. You specify the x value. Note that fixed doesn't mean that it's going to be constant always. I fix it as a specific, the experimenter fix it at a specific value. That's also why I call it mathematical variable. And the same model that is going to be the structure of the model I'm talking about will be valid or can be constructed for a bivariate normal distribution. Now let's talk about the meaning of beta 1 and also correlation coefficient a little bit. For that, I'm going to go back here. So now this part is important. Beta 1 versus correlation. Well, there is, of course, a relation. We multiply by standard deviation of y over standard deviation of x, and we obtain the other one. That's great. But what do they mean, really? Beta 1, as we have previously talked about, is actually the slope of y with respect to x. So if you change this x value by a delta x value, right? And in this case, I'm not going to be able to change x myself. But if the random variable itself changes by a delta x value, the corresponding change as the delta y value here, delta y is going to be equal to beta 1 delta x. This is what it says. That's why it's called a partial effect. It shows both the magnitude and direction of the effect. This is important. As beta 1 is greater, it means the unit change in delta x is going to be magnified by a beta 1 value. So as much as this is greater, then the change in delta y is going to be also greater. This is what is meant by beta 1. Actually, correlation is pretty much different, although they look the same, but there is that multiplying that factor makes it a bit confusing. When it comes to correlation, this shows the degree of relation between those two. What do I mean by that? This is more related with the scatter of the data. Or if I plot this bivariate normal distribution, think about those two cases. The first one is, for instance, something like this. These are the contours. And the next one is this. These are the contours. Now, this one is going to have a higher correlation compared to this one, because here correlation is going to mean, and mathematically it also means that is related with the degree of relation between those two, which means once you specify an x value here, at this point, the width of the y value here, the width of the distribution of the y value is going to be small. So you pretty much make a precise, the expected value of y here, the expected value of y given x, this estimate or the actual value, let's not talk about the estimate here, the expected value will be close to the actual value of y given x. So the actual values of y given that x value, here let's call it x0, x0 will be very much close to this value. That's what corresponds to correlation. On the other hand, here actually if we are talking about the same x0 value, as you can see, this y range is pretty much wide, right? So in this case, the y given x0 values may be pretty much distant from the expected value. But on the other hand, here for both cases, beta values, which are going to be related with those, well, actually, the peak should have been on the regression line. I drew it very poorly. Anyway, beta values, it can be such that by adjusting the standard deviation of y and standard deviation of x, the same beta values, beta 1 may be very likely to, or very well be equal to beta 2. So by adjusting these values, as I said, it is possible to make for different cases, both beta values will be identical, which would mean their partial effects will be the same. However, they have vastly different correlation values. Okay, that was the first thing that I wanted to say. The second thing is that since we have a relation such as this one, note that these are both going to be always greater than 0, right? They are the square root of variances. Now, whether beta is going to be equal to 0 or not will be totally determined by correlation. And remember, in significance of regression test, what we have tested was whether beta 1 is equal to 0 or not. Now, when it comes to correlation, let me talk about one of the conclusions about this part. Correlation is an alternative measure for the significance of regression. Depending on the magnitude of correlation, we can figure out whether the regression is significant or not. And as I said, it gives a different perspective compared to beta 1 value. Beta 1 value is more related with, as I said, with the magnitude of the effect. Whereas correlation takes also noise into consideration and how much of the whole variation in y can be explained by the other variables. It has that information inside. So correlation is going to be again between -1 and +1, which I have already talked about, I think in chapter That was chapter again in 5. All right, and this is going to again give us information about the information about the relatedness of these two variables, or in other words, significance of regression. What we have as an estimator for sigma for correlation coefficient is what we call sample correlation coefficient. It is computed by this way. We take each yi value and deviation of xi values from their sample means. We multiply them and add them together for the numerator, and we find the sum of square for xi and sum of square of yi values. We multiply them, take the square root. This is going to be an estimator for sample correlation coefficient, is going to be an estimator for population correlation coefficient. Also, numerator can be written in this form as a sum of square of xy, which I talked about previously. This is going to be sum of square of x values, and this is going to be, as I said again previously, in r square, sum of square of total terms, which actually corresponds to sum of square of y values. And you can also write it in this manner. If you obtain beta 1 hat by least square analysis, multiplying by this coefficient, right? This value is going to give you this sample correlation coefficient. Therefore, another way of finding the sample correlation coefficient, maybe first use the least square analysis and come up with beta 1 hat value, then multiply by this value and obtain this. Actually, the derivation is very simple. Beta 1 hat is simply equal to sxy over sxx. This is balanced, and when you multiply it by sxx, 1 over 2, and SST here, 1 over 2, these will be like this. 1 over 2 will be here, 1 over 2 will be here. So we are going to have SXY over this term, which is exactly this term here. So the two are that much related, but yet, as I said, they give different information on the topic. Well, one unfortunate thing is, this is not, unfortunately, simple statistics. The expected value of that sample correlation coefficient is not equal to population correlation coefficient. So R is that sample correlation coefficient is a biased estimator for population correlation coefficient. And we have another problem. The distribution of sampling distribution of R, and note that since this is a random variable, since it's a statistic, is an estimator, is going to change from sample to sample, and the sampling distribution is complicated. It doesn't obey to something that we have covered. So this is something that Fisher has come up with. We apply transformations on R to make it suit to one of the known distributions. So for those reasons, I'm not going to go into details about the, for instance, about confidence intervals for determining the population correlation coefficient. Yet I would still like to talk about the significance of correlation test here. And significance of regression via correlation can be employed using this test. The correlation is equal to 0, correlation is not equal to 0. In this case, the statistic that we use will be R times square root n-1 over 1 minus R square. This statistic itself is going to be t distributed with n-1 degrees of freedom if correlation is 0. So using this test, we can see whether there is significant relation between two random variables or not. For instance, given some population versus area data from the world's countries, you can determine the sample correlation coefficient. And then once you determine the sample correlation coefficient, you find the resulting T0 value and apply this test and see whether the relation between those two are significant or not, or any other thing that you like. As I said at the beginning, I don't know from which semester they are from, and that makes no difference actually. Now I have from the first, but they are from the same semester, so it's like there's kind of pairing here, blocking. Anyway, from the first year, these are the results. So if we plot, for instance, a histogram of the first midterms, this is what we are going to obtain. Histogram looks like this. So it is, well, not very much normal due to that left-hand side, this part here, but still that's going to be sufficiently normal for our purpose, we may say. And the second midterm is results histogram can be seen by this way. Actually, I think by the way, what's the sample size here? Let's see. Length of X, 64 grades and 64 grades, of course, here. Therefore, I think the histograms should have been with 8 bins. So maybe, yeah, still not very much normal, but I think that's pretty much sufficient close to normal. So what we can do is, first of all, plot these on scatter plot and see what they look like. All right, from maybe a larger perspective, if I adjust the limits from 0 to 100, X limits are from 0 to 100, and Y limit is also from 0 to 100. All right, let's put some grids on. So as we can see, there seems to be a correlation between those two. So X-axis is again X labeled midterm 1. And Y label is midterm 2. Now, and that's it. That's going to be a good comparison of descriptive statistics and inferential statistics. Note that if you only would like to examine the relation between those two midterms to that specific semester, you can apply all these descriptive statistical tools that we have, that I try to introduce at the very early stage of this course. But if you would like to make an inference would be like what? Assuming that these are random, this is a random sample, right? A random semester has been taken here, and that's what I did actually. And I may actually assume that I may come up with an inference that's going to be applicable for the whole population, for all semesters. So for all semesters, I'm going to be expecting a relation between midterm 1 and midterm 2, and I'm going to try to extract this information using a single sample. But that single sample, well, actually, well, as a story, this sounds fine, but I should, to make it much more statistically rigorous, which I'm not going to go into that for the time being, yet still I should maybe mention that semester to semester difference, I should analyze this, right? So actually, for all different semesters, I should be, for instance, asking similar difficult questions. And the average intellectual capacity of the students should be similar, or things like that. This should be also controlled. But for the specific case, I'm going to assume that midterm 1 results are normal distributed for all the population, and midterm 2 results are normal distributed, and they come from a common joint probability distribution. And now, as you can see, this is an observational study. I can easily find the regression line between midterm 1 and midterm 2 here. That would be, I mean, just a very simple command, fit lm on MATLAB xy. I can find this relation. So the relation is, the intercept is 34.77, and this is the x1 value, this is the beta 1 value, and r square value is 0.22. As you can see, it's a pretty much low value. And however, first we have to check the significance of regression, and it's given with this p-value. P-value of the regression is 8.16, 10 to the power minus 5. So it's a significant regression, but actually the relation between two midterms are low. That was actually a pretty much nice example also to summarize these concepts. But note that still this is an observational study. This is not a controlled study. Therefore, I cannot make an inference like midterm 1 results affects the midterm 2 or something like that. Probably there's a confounding variable here which both affects midterm 1 and 2, but there are also quite possibly other issues at hand. Anyway, so since this is an observational study, instead of this linear regression or accompanying this linear regression, I may come up with also the correlation results. Oh, by the way, one may ask, can I obtain the correlation coefficient for controlled experiments? Well, people do that, but from a strict statistical point of view, this is incorrect, because to be able to find a correlation coefficient, you should have two random variables. On the other hand, in controlled experiments, one of the variables is a mathematical variable. It's not a random variable. We perform the experiment at fixed values. So for those cases, correlation, though it's a description of the data, essentially correlation, only sample correlation is going to be a description of data. Population correlation would not mean anything there, because X values are not randomly obtained. Therefore, you cannot say that the X and Y are positively or negatively correlated. You can bring X value to anywhere that you like, but Y value will depend on that X value. Anyway, so what I'm going to do is I'm going to determine the correlation coefficient here. And in order to do that, I'm going to be using this very simple formulation. So R is equal to, let me use a better colored pen. R is equal to, let me, yi minus xi x bar. It's difficult to say the thing, so I'm going to just write it. Square yi y bar square in square root. Well, of course, on MATLAB, you can easily find this with only one command, correlation X and Y. You can find the resulting value, right? But let's find this value also using this equation. It means we are going to be taking each Y value and we are going to be multiplying by each X value, the difference from its mean value, that point and dot, the point and product means element by element multiplication. And then we are going to divide this by square root of X. Oh, I should have said here sum. Yes, I forgot that. I sum all these values. All right, then I say square root here, and it's going to be sum X minus mean X square, right? And this is going to be multiplied by, all right, sum Y minus mean Y. You should be careful about the order of the parentheses, first squaring, then summation. And the result, as you can see, is totally identical. Now, the question is whether this correlation is significant or is large enough to deem significance to this regression or not, right? This is the question. And note that, by the way, this is a positive correlation, which means that, as you can easily see, one value increases, the other one also increases. But I repeat again, you cannot infer a causation between those two random variables. So what we are going to do is we are going to be constructing this hypothesis test, whether rho is equal to 0 or whether rho is not equal to 0. Let's test this hypothesis, 0.05 confidence significance level. And in this case, the statistic that we are going to be using is r times, and I should copy here because I forgot the equation, n minus 2 divided by some square root of, 1 minus r square. And this is going to be t distributed with n minus 1 degrees of freedom. By the way, what was n here equal to? Okay, n is equal to 64 here. So here our t statistic is going to be equal to, let's find it, it's going to be correlation value. So let me write this to be equal to r. All right, it's going to be r times square root of 64 minus 62. I can write square root, of course, 62 divided by square root of 1 minus r square. So this is going to be our t0 value, and this is 4.218. It goes like this. Anyway, so I would like to find the corresponding t distribution value, right? Now, this is a two-sided test. This r could have been negative or it could have been positive. Therefore, I'm going to be interested in the t inverse 5 with how many degrees of freedom? 62 degrees of freedom. I hope, yeah. So it's 1 point is very close to 2, as you can see, since our T0 value exceeds that value. So our T0 value is equal to, let me write it on the whiteboard so you can also clearly follow. T0 is equal to 4.28 something. This is greater than T0.025 with 62 degrees of freedom, and which is equal to 0.999. Therefore, correlation, hence regression, is significant. Which means actually there is a relation between those two midterm results. On the other hand, the R-square value shows that relation is not that much pronounced, I may say. But that's another issue, as I've talked about previously about the R-square value. Now at this point, before forgetting, actually, let me also mention this, that may be something interesting. But if you take the square of R, this value is 0.232230 is actually, if we go back to the linear regression result, R-square value is exactly equal to that one. So that might seem surprising, but that R is no coincidence that we are using a capital R here, and also we had R-square. If you really take the R value, compute this one, and take the square of this term, this is going to be our R-square that we have covered in the previous lecture. So therefore, correlation, when you find the sample correlation and take the square, it's going to be R-square. That's why correlation shows the goodness of fit. But since it has a sign, it's not going to be exactly goodness of fit, because we have to get rid of, we may have a very good fit with negative value or positive value. So squaring it enables to have a statistics without a sign. Actually, it's going to be always positive. So it's going to be a more clear measure of a goodness of fit. Anyway, what I was going to talk about, okay, p-value before forgetting. What about the p-value? We are going to be trying to find here the cumulative distribution function here for 4.218 with 62 degrees of freedom. Oh, this is very, very much close to 1. So I'm going to subtract from 1 and multiply by 2 to obtain this result. Let's see, it is this value, 8 point something times 10 to the power minus 1. And here is the surprising result. This result is totally, p-value is totally equal to the p-value given by the linear regression model. What do I mean by that? I'm not going to go over that, but if you had find the beta 0 value, beta 1 value, I'm sorry, which here is found to be equal to 0.1545, and then you find the p-value for this beta 1 value, you would obtain exactly this value. And note that these are totally equal to each other because we are testing the very same thing. Whether correlation or beta 1, we are, as I said, testing the same quantity. And last of all, I'm going to draw the best fitting line so that we can see what's going on. It's always a good practice. Well, first of all, we should see the data. That's always a good practice. Visualize, inspect, visualize visually the data if you can. And once you do that, again, if you can, also see how the fitting fits to the data. So what I'm going to do is I'm going to be drawing from 10, let's see, these 2 points. I'm going to predict, use this MDL function at these 2 values. All right, yeah, with black color and dash lines. I think that would be nice. Yes. So this is the best fitting least square line, which may be used. For instance, we may say that if a person, if a student has from midterm 1, if he or she is going to, if he gets 70, the expected value of that for the second midterm is going to be something like, I don't know, 72, something like that. And also let me talk about this. If you may have used the correlation command in this fashion, not only the sample correlation estimate is given, but also the corresponding p-value also given. So MATLAB, as you can see, is very much practical with those calculations. So that's all to do that we are going to cover in this semester.